Yes, friends, from the last discussions related to the optical activity, we came to know that molecules having symmetry are said to be achiral molecules and those are optically inactive, whereas molecules which are having dissymmetry, which are having non-symmetry are said to be disymmetric molecules. Disymmetric molecules are chiral molecules and chiral molecules are optically active molecules. Yes, in general, the dissymmetry present in the molecule is due to dissymmetric carbon, that is, carbon connected with the four different valencies, which is known as chiral carbon. Thus, what we conclude from this information is, in general, in any organic molecule, if it is associated with the chiral carbons, thus it will become responsible or reason for the optical activity. Thus, molecules consisting of chiral carbons, carbon connected with four different valencies, are responsible for optical activity. But this is a general cause. Sometimes exceptions are also there, but majorly we can assume that the chiral carbons containing molecules will become optically active. Thus, the carbon which is connected with four different valencies, which is believed as reason for the optical activity of organic molecule, is known as chiral carbon. Thus, chiral carbons containing molecules are optically active molecules. Yes, organic molecules with the single chiral carbon. Here I took an organic molecule consisting of straight chain with the three carbon atoms, one acid as functional group, one OH as functional group. Thus the compound is 2-hydroxypropanoic acid. 2-hydroxypropanoic acid is having one chiral carbon. Suppose if you look at in the Fischer presentation, this carbon is connected with four different groups. This is H, this is OH, acid followed by the methyl as the groups connected with the carbon. Here also the same groups are there. Connectivity remains the same. Hence, the same molecular formula and the same connectivities containing compounds differed in orientation. Hence, these are all are said to be the stereoisomers. And here, restricted rotation is not present. They are differed at the optical rotational value, specific rotational value. Hence, these two are said to be the optically active compounds and are optical isomers to one another. Thus, it is optically active, and at the same time, second compound is also optically active. The single chiral carbon containing molecules connected with, that is, carbon connected with four different valencies. Only one chiral carbon containing molecule is optically active. And here, if you look at, if I keep a plane here, then here it is, one is acting as mirror image to the other. See here in Fischer presentation, this OH came first. It is acting as a mirror. This molecule and this molecule are acting as mirror images to one another. But I impose this particular molecule over this. It never superimposes. So therefore, these are non-superimposable mirror images. Non-superimposable mirror images, that is, optical isomers which are non-superimposable to one another are said to be enantiomers to one another. These are known as enantiomers. Yes, first molecule is dissymmetric molecule. First molecule is having chiral carbon, carbon connected with four different valencies. It is having one specific rotational value, whereas the rearrangement related to the bonds can be readjusted in three-dimensional space in such a way that it can give another one compound, whereas one compound is acting as mirror images to the other compound. But if I superimpose the molecule of the second molecule over the first molecule, acid group and the methyl group are superimposed. But whereas on superimposition, H and the OH will overlaps with one another, that is not the imposition. That is imposition, but that is not the superimposition. Hence, non-superimposable mirror images which are optically active as per dissymmetry is concerned, such kind of optical isomers are known as enantiomers to one another. And the conclusion is, single chiral carbon containing organic molecules are always optically active. and the number of optical isomers can be given with a formula. Can be given by 2 power n, where n stands for number of chiral centers here, and that will becomes equal to 2. Out of these two, one is mirror image of the other, and these two are non-superimposable one another. Hence, these two are having a relationship. That relationship is said to be enantiomeric relation. Hence, these two, which are non-superimposable one over the other, are known as enantiomers to one another. Now we will discuss the case number 2, that is optical isomers with 2 chiral carbons. Yes, 2 chiral carbons containing molecules. One of the example is 2,3-dihydroxy pentane is the example, whereas this particular carbon is connected with 4 different valencies. The third carbon is also connected with 4 different valencies like hydrogen, OH. This side it is having OH containing ethyl group, non-OH containing ethyl groups, etc. Thus here we are having 2 chiral carbons. This is one chiral carbon, and at the same time third carbon is also chiral carbon. Now we will look how many number of optical isomers are possible and in which way they are related with one another. What is the relationship? Now here if I write the Fisher presentation, now here I am considering, here it is methyl group, and here it is connected with 2 chiral carbons followed by one OH is present towards the right, other OH is also present towards the right. This is number 1. Whereas I can write another one isomer, whereas stereochemistry can be adjusted in such a way that at third carbon the stereochemistry is differed. Now here this is OH followed by this is ethyl, and remaining 2 are the hydrogens. Consider this is molecule number 2. Whereas another one isomer, here also I am expecting methyl is there, here ethyl is there. Instead of keeping the first OH towards the right side, here I am keeping left side followed by this is OH, remaining are the hydrogens. And the last case, here all possibilities I am writing, whereas methyl as well as ethyl is top and bottoms, followed by here OH is towards the left, OH is towards the left, and this is H and H. In these molecules here you never find any kind of plane of symmetry, you never find any kind of other symmetry elements. Every molecule, every representation, every possible representation is an asymmetric representation, hence everything is optically active. Here it is having 2 chiral centers, it is also having 2 chiral centers, having 2 chiral centers, having 2 chiral centers. Containing molecule can be adjusted in 4 different ways. Out of those 4 ways, nothing, no molecule is symmetrical, no molecule is having plane of symmetry, center of symmetry, inversion plane of symmetry, nothing is present. Every molecule is dissymmetric, implies every molecule is optically active. Thus here, for the asymmetric molecule, otherwise different ends containing molecule having of n number of chiral carbons, the number of optical isomers can be given by number of optical isomers. That can be given by 2 power n, the formula, whereas 2 is to n stands for number of optical chiral centers. 2 power 2 will becomes equal to 4. 4 optical isomers are obtained, and these are the 4. Out of these 4 there are relations. Let us see the first one as well as the fourth one. Yes, if you keep a mirror between first and fourth, after keeping a mirror, the first one appears like this. That appearance is nothing but what? Fourth one. So therefore first and fourth are mirror images to one another. So therefore here I will write the images, mirror images. What are mirror images here? 1 and 4 are mirror images to one another. So similarly for 4, 1 is also mirror image. Similarly for second and third, if I keep a mirror here, the OH comes over here, H comes over here, this molecule once again reflects over there. So therefore 2 and 3 are mirror images to one another, and these mirror images are non-superimposable one over the other. Suppose if I want to keep this fourth structure over the first structure, that imposition doesn't reflect the superimposition. That is, every particular connectivity present in fourth is not exactly as it is that is present in the case number 1. Such kind of like this superimposition, these two are images to one another. Let us see, this is my molecule, and here it is its mirror image, and if I impose, it appears like this, but it is not superimposition because little finger followed by the the thumb finger, and here other fingers not at all having any kind of imposition. This is superimposition. But thing is, this is not the superimposition. Superimposition does not occur. Hence 1 and 4 are said to be enantiomers. Similarly, 2 as well as 3 are said to be enantiomers. Thus here we are having two pairs of enantiomers. 1 and 4 a pair of enantiomers. Similarly 2 and 3 a pair of enantiomers. And whereas the relation between 1 with respect to 3, 1 with respect to 2 is diastereomeric relation. Similarly 4 with respect to 2, 4 with respect to 2, 3, these two are also diastereomeric pairs. If I write the list of the things, yes, in this molecule, here what we are getting is, after looking at the structures, here what we are getting is 1 and 4, these are enantiomers. 2 as well as 3, this is also enantiomer, whereas 1 with second and third, both these are diastereomers. Similarly 4 with second and third, these are also diastereomers. In that way relationship is present. Thus here two chiral carbons containing unsymmetrical ends containing organic molecule is having 4 ways of arrangement of 3-dimensional valencies. In such a way it results 4 asymmetric molecules. 4 are optically active. Out of those 4, 2 are acting as enantiomers to one another. That is, we will be getting 2 pairs of enantiomers. Those pairs are here 1 and 4. Similarly here 2 and 3. Whereas with respect to 1, second is maintaining diastereomeric relation. With respect to 1, third is also maintaining diastereomeric relation. Similarly with respect to 4, second is diastereomer. With respect to 4, third is also acting as diastereomer. That is optical isomer, whichever is not maintaining enantiomeric relationship, then such kind of other isomer relationship is known as diastereomeric relationship. That is optical isomers which are non-superimposable mirror images to one another. That should be mirror image, but that mirror image, if it is non-superimposable, that is known as enantiomer. Whereas optical isomers which are not maintaining enantiomeric relationship, those are known as what here? Diastereomers. Let us go for another one organic molecule having symmetrical ends with 2 chiral carbons, that is 2,3 dihydroxybutane. If I write the structure of 2,3 dihydroxybutane, this is 2,3 dihydroxybutane, whereas this end it is consisting methyl, this end also it is consisting methyl. From the mid, this is first half and this is second half. Thus here it is maintaining similarity, similar ends associated organic molecule having more than one number of chiral carbons. If I write the corresponding Fischer presentations, this is OH and this is OH, and remaining is H and H. Similarly, if I write the another Fischer presentation, this is OH and this is OH, and if I write another Fischer presentation, this is OH and this is OH. If I write the another Fischer presentation, this is OH, this is OH, and these are H. These are the possible ways of adjustment. This is structure 1, this is structure 2, this is structure 3, and this one will be the structure 4. In this case, here in this molecule, first one, molecule is not a asymmetric molecule, this is a symmetric molecule, because if I keep a plane in the mid, then the first half of molecule is acting as mirror images to the other. Hence, plane of symmetry is present, molecule is becoming optically inactive. Similarly, if I go for the fourth structure, here also plane of symmetry is present. So, plane of symmetry is present implies what? Here also this molecule is becoming symmetric molecule, hence it is not having any kind of optical activity. Whereas in structure number second and structure number third, there is no plane of symmetry, hence molecule will become optically active molecule. Thus, second molecule is optically active, third molecule is optically active. And moreover here, in case of this particular molecule, here these two are acting as mirror images to one another. How these are acting? These two are acting as mirror images to one another. Thus we are having total 4 optical isomers. Out of 4 optical isomers here, 2 of them are optically inactive, though they are having chiral carbons, but they are having symmetry within the molecule. and remaining two molecules are optically active, and those two are mirror images to one another, and those are non-superimposable mirror images, hence those are acting as enantiomers. Thus we are having here the optically inactive molecules, though having chiral carbons, are known as meso molecules or the meso compounds. Organic compounds having chiral carbons, having ability to show the optical rotation by maintaining chiral carbons, but due to symmetry adjustment of chirality, symmetrical adjustment of valencies on the chiral carbons, molecule is having symmetry. So molecule becomes symmetrical though it is having chirality and it is optically inactive. Such kind of molecules are known as meso kind of molecules. In case of meso molecules, the mirror image is not at all considered as another isomer, because here it is optically inactive, so therefore it is just considered as one meso compound. Thus here we are having total optical isomers, though it is 4. What we will consider is this inactive and mirror image of this inactive, though I can give this one as mirror image and this one, both are considered as same molecule, not as different molecules. Thus total I am having 2 plus these two are considered as 1, hence here 2 plus 1 is equal to what? 3 optical isomers are possible. Out of that 3, a set of 2 are acting as enantiomers, those are optically active, and another one is said to be what? Meso compound to one another. Thus the formula used for the calculation of number of optical isomers followed by total number of optically active isomers and the inactive isomers can be counted as number of optical isomers. Number of optical isomers can be given by 2 power n minus 1 plus 2 power n by 2 minus 1, whereas this 2 power n minus 1 are number of enantiomers, whereas these are number of meso compounds. Number of enantiomers of this particular compound can be given by 2 power 2 minus 1, that will becomes equal to 2 power 1 is equal to 2. 2 enantiomers are there. Number of meso compounds can be given by 2 power n by 2, 2 by 2 minus 1, that is 2 power 1 minus 1 is equal to 2 power 0 is equal to 1. So therefore total number of optical isomers are 2 plus 1 will becomes equal to how much here? 3. So therefore the formula used for calculation of number of optical isomers in case of symmetrical ends containing even number of chiral carbons containing molecule can be given by 2 power n minus 1 plus 2 power n by 2 minus 1, whereas this 2 power n minus 1 represents the number of optical isomers and half of them will become number of optical isomers, that is pairs enantiomers, whereas remaining optical inactive isomers can be given by 2 power n by 2 minus 1, which will becomes equal to 1. Here 1 is mesomeric compound. Thus this particular first term represents the total optical active isomers, and this is optical inactive isomer. So therefore total optical active plus optical inactive isomers will becomes equal to total number of optical isomers. This optical inactive isomer is said to be the meso isomer. These of all are having enantiomeric relation with one another, hence these are said to be the enantiomers. If you want to get the enantiomeric pairs, half of this particular total number of enantiomers will becomes equal to enantiomeric pairs coming from this particular molecules having symmetrical ends with the even number of chiral carbons. Yes, let us go for the next case, that is symmetrical ends containing odd number of chiral carbons associated molecule and its corresponding optical isomers and their relations. A symmetrical ends implies ends will be symmetrical. From the middle, the first half and second half appears to be same to one another. Such kind of molecules are symmetrical molecules and symmetrical ends containing molecule from the mid. And here it is consisting 3 chiral carbons. Officially those 3 chiral carbons are like this, and here it is having 1 chiral carbon here, 1 chiral carbon here, another 1 chiral carbon here, connected with 4 different groups. Such kind of molecule is 2, 3, 4 trihydroxypentane is the molecule. In this molecule now we will count the number of optical isomers, theoretically eligible optical isomers, practically different optical isomers and their interrelation, and in that optically active isomers and optically inactive isomers, and the formulas generalization to count the number of various types of substances involved as per the molecule consisting of symmetry in association with odd number of chiral carbons. Yes, optical isomers with 3 chiral carbons having symmetrical ends. Here I am taking the molecule that is 2, 3, 4 trihydroxypentane. All varieties, all stereoisomers I am expecting. Second, third, fourth, 3 carbons are chiral carbons. So therefore 3 OHs are there in Fisher representation. I wrote 3 towards the right side, 2 towards the right side, followed by last one is towards the left, second one, and the variation comes for the second carbon. Second carbon related OH is written towards the left, followed by third is right, left followed by third is also left. And similarly here, by keeping all varieties reverse to this, suppose if I keep all of them towards the left, whereas all left followed by last but one is right, whereas here the second one is at the right followed by all are left, and the second is right followed by next is right. Thus all 8 whichever are possible, I wrote 8 out of them, 8 which are theoretically possible. In that theoretical possibility, as being it is maintaining symmetrical ends, what happens is the in plane 180 degrees results the same compound. So some of the compounds are meso compounds are having plane of symmetry. Let us go for the first connectivity. In this first connectivity, what happens? If I feel along with the third carbons H and OH, if plane is present, then this plane bisects the molecule into 2 equal halves. Thus it is optically inactive. This compound is said to be the meso compound. Similarly here the third molecule, here also the H and OH connectivity related carbon linkage is considered to be present on the plane. Along with that plane, the top half as well as the bottom half are mirror images to one another, hence it is optically inactive. This is also meso compound. Whereas remaining 2 meso compounds appears here as this one is meso compound and this one is meso compound. But whereas in these meso compounds, this is acting as mirror images to this, and this particular compound which is meso compound is acting as mirror images to this. So therefore here these connectivities and these connectivities are same, and these are optically inactive mesos. Hence these two combination is not considered as 2 different varieties. These two are considered as same. Similarly here the another meso compound, this is meso and this is also meso. Connectivities are same, H and OH, H and OH. Yes, here OH, H, OH is present, OH, H, OH is present. Similarly H, OH, H, H, OH, OH. In plane 180 degrees rotation will result this carbon bottom, this carbon top, followed by these valencies towards the left side, or these valencies towards the right side, or these. Hence these 2 compounds are not considered as the different compounds. This set of 2 compounds are same, hence one compound. This set of 2 compounds are not different, hence the same compound. Hence we can consider, though theoretically we are feeling that there are 4 meso compounds, those are not 4 meso compounds. 2 different connectivities containing 2 meso compounds are present. In plane 180 degrees rotation of every molecule results in Fisher the same molecule. Hence this particular structure and this particular structure are same. And the same rule is applied for the active compounds also. Suppose if I come for the second molecule and the fourth molecule, in plane 180 degrees rotation, yes, this methyl comes over, this methyl goes up, and these right side valencies are adjusted at the left side. So therefore this H at the right bottom will becomes top left, and this middle is middle, whereas this right top is converted as left to bottom is OH. Similarly the same thing happens here. These 2 molecules are not different. Similarly these 2 molecules are not different. Thus I am writing this is optically inactive, this is optically active, and this is optically inactive, and this is optically active, this is optically inactive theoretically, this is optically active, this is optically active, whereas this is optically inactive. In case of optical inactivity, we are getting 4 out of 4. That is nothing but what? One molecule is represented in 2 different ways, hence those are 2 different molecules. So here I am writing meso compounds appears to be 4, but these are not 4, 2 different compounds. Similarly active compounds are also appears to be 4, but these are not 4. These are nothing but what? The 180 degrees in plane rotation of 2 different molecules, and these are also considered to be how many here? 2. Thus we will formulate this particular number obtained tentatively in the form of a logical relation with respect to the number of chiral carbons with the symmetrical ends. Thus we will calculate number of optical isomers and number of meso compounds, number of enantiomers and number of enantiomeric pairs present in the molecule having symmetrical ends in association with odd number of chiral carbons. Thus, the tentative mathematical relation between the number of isomers, the total number of stereoisomers including optically active as well as optically inactive, that can be given in case of symmetrical ends containing odd chiral carbons containing molecule is 2 power n minus 1, and in this case that is 2 power 3 minus 1. 3 minus 1 is 2. 2 power 2 is equal to what? 4. 4 isomers, 4 different stereoisomers are obtained. Theoretically you will be getting 8, but those are not 8, these are just 4 only. Whereas in that the number of optically active isomers can be given by total isomers minus meso isomers. Let us go for the meso isomers. Number of optically inactive isomers due to internal compensation due to plane of symmetry in case of symmetrical ends containing molecule can be given by 2 power n minus 1 by 2. N is odd number, odd minus 1 is even, even by 2 is once again a number. Thus you can remember total number of meso isomers, optically inactive isomers can be given by 2 power n minus 1 by 2. 2 power here 3 minus 1 by 2. 3 minus 1 is 2. That is 2 power 2 by 2 is equal to 2 power 1 is equal to 2 meso compounds are obtained. Now here total isomers are 4. In that inactive isomers are 2. So total isomers 2 power n minus 1 is 4. Inactive isomers, meso isomers are 2 power n minus 1 by 2. That is once again 2. 4 minus 2 is equal to 2. This is total number of optically active isomers. Thus we can correlate the formulas and we can write the formulas in such a way. If molecule is having unsymmetrical ends, then one formula is enough. Molecule is having symmetrical ends, it can associated with even number of chiral carbons, it can associated with odd number of chiral carbons. Thus formula varies. We will write a table related to the tentative formulatical or formula based relation of number of isomers and the number of total number of stereoisomers, total number of optical active isomers, total number of meso isomers. In case of asymmetric molecules, symmetric molecules having even number of chiral carbons as well as odd number of chiral carbons at once. Yes, as we know, if molecule is symmetrical, any of the symmetry element is present like plane of symmetry, center of symmetry or improper axis of symmetry, that molecule is symmetrical, molecule is optically inactive. Now we are discussing optically active molecules related information, and logically that molecule are said to be asymmetric molecule. Asymmetric molecule having unsymmetrical ends, ends are different, and asymmetric molecule is having symmetrical ends. Whereas in case of unsymmetrical ends, though it may be consisting any number of chiral carbons, the total number of stereoisomers, all stereoisomers are optically active isomers. So therefore total number of carbons here I am considering it as n. N may be even number, n may be odd number. The total stereoisomers will becomes equal to 2 power n, where 2 is a number, n stands for total number of chiral carbons. Here all are optically active. All are optically active. There is no meso compound, there is no inactive isomer. Every isomer is optically active. And here one is enantiomer to the other, thus we are having 2 power n minus n by 2 number of enantiomeric pairs are present. Whereas if the case comes towards the symmetrical ends containing molecule, formula varies, because even number offers some relation, odd number offers some relation. Because if it is even number, plane goes from the mid of the carbon-carbon connectivity, whereas if it is odd number, plane goes through the carbon connected with 2 valencies combination. So therefore if it is having even number of carbons, then here what happens is, if it is having even number of carbons, total number of optically active isomers that can be given by 2 power n minus 1. Total number of inactive isomers will becomes equal to 2 power n by 2 minus 1. Total number of stereoisomers will becomes equal to optically active plus optically inactive, that will becomes equal to 2 power n minus 1 plus 2 power n by 2 minus 1. Thus here these are meso compounds and these are optically active compounds. One is acting as mirror images to the other. These are total enantiomers, total number of optical active compounds, total number of inactive compounds. The total active plus inactive will becomes equal to total number of stereoisomers, that will becomes equal to 2 power n minus 1 plus 2 power n by 2 minus 1. If it is consisting odd chiral carbons, then here there is a slight variation. the total isomers will becomes equal to 2 power n minus 1. Total active plus inactive. Whereas in that inactive isomers will becomes equal to 2 power n minus 1 by 2. N is odd minus 1 is even by 2 is one second number. Thus calculation becomes easy. Remembrance also becomes easy. Whereas total number of active isomers can be given by 2 power n minus 1 total minus meso. 2 power n minus 1 minus 2 power n minus 1 by 2 will becomes total number of active isomers. 2 power n minus 1 by 2 is total number of inactive isomers, and total number of stereoisomers will becomes equal to this plus this, and here it is addition subtraction cancels one another, that will becomes equal to 2 power n minus 1. Thus unsymmetrical ends containing all are optically active. There is no meso compound, there is no inactive compound, that is 2 power n. If it is having symmetrical ends, then even formula, even number of chiral carbons containing formulas related to the number of active 2 power n minus 1, number of mesos 2 power n by 2 minus 1, total 2 power n minus 1 plus 2 power n by 2 minus 1. If it is odd, total stereoisomers are 2 power n minus 1, meso isomers are 2 power n minus 1 by 2, total active isomers are 2 power n minus 1 minus 2 power n minus 1 by 2. These of all are made clear in these previous examples by taking one chiral carbon, two chiral carbon with symmetrical ends, unsymmetrical ends, and the odd chiral carbons containing unsymmetrical as well as the symmetrical ends. Yes, the table and related to the formulas once again to your notice. Yes, if it is having unsymmetrical ends, total number of stereoisomers are 2 power n, all are optically active. If it is having symmetrical ends with even number of chiral carbons, number of active can be given by 2 power n minus 1. Number of inactive mesos can be given by 2 power n by 2 minus 1. Total can be given by sum of these two. Whereas if it is having odd number, then what happens is the total number will be given by 2 power n minus 1. Mesos can be given by 2 power n minus 1 by 2. And active can be given by total minus mesos. Like these formulas are present. Now we will go for some more technical terms. Enantiomers, diastereomers, meso compound, racemic mixture, followed by their corresponding absolute rotational values and the tentative relation between rotational values in between the enantiomers and the racemic mixture as well as the meso compounds. Let us go for some more technical terms, that is active compound. Yes, a symmetric molecule is generally optically active, and every asymmetric molecule is not having any kind of major symmetry elements like plane of symmetry, center of symmetry, improper axis of symmetry. It can rotate the plane polarized light, hence it is optically active. Whereas whatever the rotational value is coming as a result of keeping the compound in the polarimeter is corresponding optical rotational value. Whereas that optical rotational angle is made constant under some specific conditions of unit, that is 1 decimeter path length followed by 1 gram for 1 ml concentration solutions, and that is said to be what? Specific rotation. It is having specific rotation. Specific rotation is constant. If I maintain the same plane polarized light as well as the same temperature, that's what this rotational value under specific conditions is constant, hence that rotational value is said to be specific rotation. Let us consider it's one of the compound is having specific rotation of plus x degrees. Plus x degrees is the specific rotation. Whereas inactive compound, if it is symmetric molecule, though it is having chiral carbons, it will become optically inactive. Thus having chiral carbons but becoming optically active due to some symmetry elements present in it, such kind of compounds are said to be optically inactive compound. Such kind of having eligibility to show optical activity, but due to some special reasons of symmetry it becomes optically inactive, are said to be meso compounds. And that meso compound is optically inactive, as being it is optical rotation, optically inactive, its rotational value is 0, hence its specific rotational value is also 0. So therefore its corresponding specific rotation is 0 degrees. Every 0 degrees specific rotation containing compound is known as optically inactive compound. If it is having chiral centers, then that is known as what? Generally meso compound. Inactive is a general word. In inactive, without any reason, general inactive, no chiral carbon is there, just it is inactive. Having chiral carbon followed by inactive, that is said to be what? Meso compound. Yes. In case of active compounds, our discussion is regarding active compounds. I am having compound A is a compound and B is also a compound. Both are optically active. Whereas these two are having a relation in such a way that one is acting as mirror image to the other. Yes. Compound A, compound B, both are optically active compounds. Both are stereoisomers. Both are optically active stereoisomers. And both are acting as mirror images to one another. So if I keep mirror image before A, it appears as B. If I keep mirror before B, it appears as A. One is acting as mirror images to one another, and whereas one is non-superimposable over the other. If I superimpose, so it appears as mirror image. If I keep B as it is and overlaps with the A, it doesn't overlaps 100%. Such kind of imposition doesn't gives perfection. That is said to be non-superimposition. Such kind of nature containing compounds are named with a relation one with other as enantiomers. It is having some specific rotation. Let us consider it is having some specific rotation plus x degrees. Whereas the other compound is having specific rotation, that is also x degrees, but that is minus x degrees. Thus, the enantiomers are optically active. The corresponding specific rotational value, quantity remains, magnitude remains same. That is, quantity remains same. That is, but the quantity magnitude remains same, but the sign convention value is opposite. Its specific rotation is some plus x degrees. Its specific rotation is minus x degrees. Suppose its specific rotation is not x. If it is plus y degrees, it will becomes minus y degrees. Because these are mirror images. If it rotates towards the right, it will rotate towards the left. If it rotates towards the left, it will rotate towards the right. Such kind of relations are there. Such kind of compounds are said to be enantiomers to one another. So enantiomers are, two conditions are definitely has to be followed. First of all, these are optically active isomers. Second, these are mirror images to one another. Third, they can't be superimposed one over the other. If such relations are valid, then those compounds are said to be enantiomers to one another. If I take a 1:1 ratio of enantiomers, then that mixture is said to be what? Racemic mixture. Yes. Here if I take a 50-50, 1:1 ratio of racemic mixture, enantiomers, then that will become optically inactive due to external compensation. One cancels the other. Such kind of 1:1 ratio, 50-50 ratio of enantiomeric mixtures is said to be the racemic mixture. Yes, there is a special word, that is diastereomer. Then what is meant by diastereomeric relation? Diastereomerism is a relation present between one stereoisomer with the other stereoisomer, similar to that of the enantiomerism. In between two stereoisomers, a particular relation is said to be enantiomerism. In the same way, in between two stereoisomers, a particular relation, if it is existing, then that is said to be what? Diastereomerism. So here if I take the isomers, stereoisomers, one particular variety of stereoisomer is enantiomerism. For one particular compound, only one mirror image is there. There is not more than one mirror images. So therefore, for one compound, one enantiomer is there. Whereas, if I take a compound consisting of more than one chiral carbons, it is having many stereoisomers. If I take one stereoisomer here, A, yes, A is having B, C, D are the other stereoisomers. Let us feel as above that A and B are enantiomers to one another, whereas this is optically active, this is optically inactive. Like this is a meso compound, this is optically active compound. Now with respect to A and C, with respect to A and D, that relation is said to be diastereomerism, and those isomers are said to be diastereomers. That is stereoisomers whichever are not enantiomers. I wrote all stereoisomers. Out of them, with respect to A, B is enantiomer. Only one enantiomer is present. Remaining all are what? Diastereomers with respect to A. So therefore, stereoisomers whichever are not enantiomers to one another, then with respect to one particular compound, the remaining all compounds will become diastereomers to one another. Or stereoisomers whichever are non-enantiomers, not enantiomers, then those are known as what? Diastereomers. There may be more than one diastereomer in a particular stereo compound. Stereoisomer A is having here C, diastereomerism, with D, diastereomerism. Diastereomers may be both optically active. Yes, here A and C are optically active. One may be optically active, one may be optically inactive. Both may be optically inactive. Yes, in the last case we got two meso compounds. those two meso compounds are also said to be what? Diastereomers to one another. Thus, here diastereomerism is not having a specific definition. Optical isomers, otherwise stereoisomers, whichever are not the enantiomeric relationship with one another, then those are said to be having a diastereomerism or diastereomeric relation with one another. Whereas here, suppose if it is A is having plus x degrees as the rotation, B is having its corresponding enantiomer, it is also having x degrees, but that is minus x degrees. C is not the enantiomer of A, so therefore it is having some rotation, either plus or minus, that is y degrees is the rotation. D is not having any kind of rotation, its corresponding rotational value will becomes equal to what? 0. Such kind of compound is said to be what? Meso compound. Whereas relation of A with respect to A, such kind of relation is said to be homomer relation. Yes. A with respect to A, if I expect, then that relation is not enantiomer relation, that relation is not diastereomer relation. This relation is known as what? Homomeric relation. Same compound with itself is having a special relation is said to be homo relation. A same compound followed by non-superimposable mirror image relationship. If both are optically active, then that is known as enantiomeric relation. Stereoisomer, whichever are not enantiomers, then those of all are known as diastereomers. Out of diastereomers, both may be optically active, both may be optically inactive, one of them may be optically active. If they are optically active, their rotational values are different. If they are optically inactive, both are having 0. If one of them is optically active, one is 0 and one is other. Whereas one is x and other is minus x, then those two are said to be what? Enantiomers to one another. Thus, we made the discussion related to the active compound as well as inactive compound and especially meso compound, and what is enantiomers and what is racemic mixture, what is diastereomer, what is specific rotations related quality information regarding enantiomers, diastereomers, meso compounds as well as the racemic mixture. And the last point, in case of racemic mixture, 50-50 ratio of enantiomers are taken, one cancels the other, the net rotation value is found to be how much here? 0. Whereas here this 0 degree specific rotation is due to external compensation, one cancels the other. So therefore, one is externally cancelled by the other, hence it is said to be what? Racemic mixture. Whereas in case of meso compounds, here what happens? Here, top one is optically active portion, bottom one is optically active portion, it want to rotate towards the clock, it want to rotate towards the anti-clock. Thus, one half is cancelled by the other. Internally within the molecule, compensation occurs, reverseness occurs, opposition occurs. Hence, optically, a meso compound is optically inactive, net rotation value is 0. That 0 is due to what? Internal compensation. And in the next class, we will discuss the features related to the enantiomers and the features related to the racemic mixture and its separation, features related to the diastereomers, and we will go for examples to identify total number of stereoisomers, total number of optically active isomers, optically inactive isomers, meso compounds, and the interrelation between them. Question for you, that is on monochlorination, that is isobutane system is expected to undergo monochlorination. One chlorine is substituted, then you are asked to write the all varieties of compounds obtained and the interrelation between them. Let us see here. Here this is primary carbon, primary carbon, primary carbon. These two primary carbons are same, and this is secondary carbon and this is tertiary carbon. Out of those three primary carbons, two primary carbons are same. Hence either I may substitute at this place or at this place, that results the same compound. But this will be different, secondary is different, tertiary is different. I will write for the primary first. Then I will identify the stereo chiral center and I will identify the number of isomers present in it. If I replace one of the primary hydrogen with chlorine, this is one. And if I replace another one primary carbons hydrogen with chlorine, this is the compound. If I replace secondary with chlorine, this is the compound. If I replace one of the tertiary hydrogen with chlorine, this is the compound. Whereas in this compound, here it is having two hydrogens, here it is having two hydrogens, here it is having two methyls followed by hydrogen, and here it is having three hydrogens, and these are same. Three hydrogens, three same groups optically inactive, non-chiral center. Two same groups non-chiral center, two same groups non-chiral center, non-chiral, this molecule is optically inactive. Let us go for this molecule. Here this and this are having similar groups, but whereas if you come for this, here it is having hydrogen here. Here one side methyl, one side ethyl, one side chloromethyl, and in one side hydrogen. Hence this center is chiral center here. Substitution occurred over here, but this was become chiral center. And in this case, here this particular carbon atom is having hydrogen. 4 different groups are there. That is also chiral. And in this case, here though it is chlorine is substituted here, 2 methyls are same. Hence it is not having any kind of chiral. And here 2 hydrogens, achiral, 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 achiral. So therefore this is also optically inactive. Thus I am getting 4 different structural isomers in such a way that this is different one, this is different, this is different, and this is different. For me these are the 4 structural isomers. Out of these 4 structural isomers, here 2 are optically inactive and 2 of them are optically active. Whereas wherever the optical activity comes, yes, here this center is having 2 varieties of relations. It can have R in configuration and its mirror image S in configuration. I will explain what is meant by R, what is meant by S. Suppose if I am saying it as 2A followed by 2B is there. One is R in configuration and one is S in configuration. Similarly here 3 is there. I am saying one of them as 3A, one of them as 3B, and one is R in configuration and one is having S in configuration. And this is 1 and this is 4. These are the compounds and the relations present between the compounds. 1 followed by remaining all. What are these? And 2 followed by R. So optically active followed by optically inactive. Yes, 1 and 4 are optically inactive and these are all are optically active. Whereas 1 with respect to remaining all are structural isomers. 1 with respect to 2A, 1 with respect to 2B, 1 with respect to 3A, 3B, 1 with respect to 4. All are structural isomers to one another. Within 2A and 2B are enantiomers to one another. 3A and 3B are enantiomers to one another. Whereas 2A with 3A, diastereomer. 2A with 3B, diastereomer. 2B with 3A, diastereomer. 2B with 3B, diastereomer. Whereas 3A and 3B are enantiomers to one another. Thus, the relations that I can write in between the optically active isomers, suppose 2A followed by 2B, these are enantiomers. Whereas 3A followed by 3B, these are enantiomers. Whereas 2A with either 3A or 3B, these are diastereomers. Similarly here, suppose if I am taking 3A, for 3A, 2A and 2B are diastereomers. Similarly for 3B, 2A and 2B are diastereomers to one another. These are called diastereomers. Such type of interrelations are present between the stereoisomers obtained as a reaction product in case of isobutane on monochlorination. The corresponding different varieties of compounds and their optical active relation, optical inactive relation, followed by corresponding number of stereoisomers, structural isomers. If they are stereo, the corresponding interrelation between them, that is enantiomeric relation, diastereomeric relation, and there is no meso compound, and pairs of enantiomers. 2A and 2B is a pair of enantiomer. Similarly, 3A and 3B is a pair of enantiomers to one another.